Alright, you guys want to say hi to Ian and Ethan?
No.
Okay. Alright, so today we're going to talk about the accumulation function, and the F2C is the fundamental theorem of calculus. Do you guys remember the fundamental theorem of algebra? No.
Yeah.
What did it have to do with? It had to do with finding zeros, but that's fine. That's what algebra is all about. Anyway, so we're going to talk about accumulation functions first. And you guys actually have already learned all these things on the accumulation function. You're just going to have some different notation that you might not have seen before. So for the area, oh, it does not look good. That's okay. So an accumulation function outputs the area under the curve from some starting value, and then I have the wrong word here. It should say from some starting value to x, which is the input. And this right here is an example of an accumulation function. We'll have something of x equals and then the rest of it. So we're going to kind of write that up here. We're going to say f of x equals, and then we're going to have the integral symbol. The lower limit is going to be c. That's the starting value. And then on these accumulation functions, the upper limit is x. And it should match whatever is here. And that's the independent variable. Alright? And then you'll have something like f of t dt. And then f of t is the rate of accumulation. And we actually kind of did this. The very first day we talked, we were accumulating snowfall. But like I said, it's the first time I think you're seeing that notation when you're going from something to x. Alright. And that leads us straight into, bless you, the fundamental theorem of calculus, the first part. There's two fundamental theorems of calculus. So this is the rate of change of an accumulation function. So when you guys hear rate of change in a calculus class, what do you think? That's what you think in the algebra class. The slope. No, you're right, it's fine. What is it in calculus? Derivative. So what we're going to be, the fundamental theorem of calculus is all about finding the derivative of an accumulation function. The rate of change of an accumulation function is finding the derivative of an accumulation function. And using the first part of the fundamental theorem of calculus, it's, I don't want to say easy, but the idea of it is very simple, that you're going to feel like you're not doing the right thing, because it's really not a big deal. So a derivative is going to undo an integral, and vice versa. But really the only thing that happens is when you take the derivative of this, it just changes the variable to x. So the derivative of the integral from z to x of f of t dt is just going to be f of x. And we're going to do a couple of these, and you'll see that it's really not a big deal. And we're going to do a proof of it at the very end. Okay, so the first thing we're going to do on our check for understanding is to evaluate this accumulation function. So h of x is this. We want to find h of 2. So h of 2 means to find the integral from -2 to 2 of f of t dt. And that just means we're adding up the areas from -2 to 2. So,
Where did you get -2?
right here.
Oh.
Alright, so we're going to start at -2, we're going to end at +2, and this is just telling us to add the areas between -2 and 2. So this is a triangle. The base looks like it's 4, the height looks like it's 4, so what's the area of that triangle? 8. So all that is 8.
Will you ever be asked like that without a graph?
You might be asked that with a table. Later, you might be asked that with a function. We just don't know how to find the integral right now. We will, don't worry. Alright, let's find b. We're going to find h of 8. So same thing, we're going to do the integral from -2 to 8 of f of t dt, which is adding areas. We want to go all the way to 8 though. Now one thing I noticed about this from 6 to 8 is that it's below the x-axis. So what do we do for those areas? They're negative, or you subtract them. Alright, to me this looks exactly like that. So that's going to be 8 also. Alright, and this is half of that same triangle. 4, but it's going to be -4 because we're below the x-axis. So to find that, to accumulate those areas, we're going to add 8 plus 8 minus 4. Oh, and that's where you have 12. Yes. So that's not really new. It's just notation. Don't be surprised that if on your quiz today you're adding areas and you get something underneath the x-axis. So be real careful. That's down there. It's negative. Okay, C. C is pretty much the fundamental theorem of calculus part 1. We're going to find h prime of 8. So let's talk about what h prime of x is. H prime of x is the derivative of that accumulation function. So we're going to take the derivative of the accumulation function from -2 to x. All it does is it just changes it to f of x. And this right here is the graph of f. So if we're asked to find h prime of 8, they're asking us to find f of 8. You guys have been able to find f of 8 for a long time. So looking at the graph of f, what is f of 8? -4, and that's it.
What the?
I know, it's crazy.
Wait, how do you know that when you're looking for prime, you just go to f?
Well, because we know that this is f, and this is h. So we want the derivative of h. It's this right here, which is that fundamental theorem of calculus, where that derivative kind of just knocks off the integral, and you're just left with f. Okay, and then D asks us to find the second derivative of h. So h double prime of 6. So let's talk about what h double prime of x is. We know that h prime of x is f of x. So what do you guys think about h double f prime of x? And if we're looking at the slopes and we're finding the derivative, oh, I told the answer. Shoot. If you're looking at the graphs and you're finding the derivative, you're just looking for the slopes.
Slope.
Alright, so if we're doing h double prime of 6, we're doing f prime of 6, which is really the slope of the graph when x is 6. What do y'all think? Hard negative, but negative 2. I'm going to be a little more specific right here where I wrote slopes. It's technically slopes of the graph of f. Alright guys, so on number 2, this is straight up fundamental theorem of calculus. So we have a y is this accumulation function, and we want to find dy dx. So we want to find the derivative of y. All it does is we're going to have this integrand, but instead of t, what do we write? X. That's it. That is how you use the first fundamental theorem of
There
calculus.
is no way that's it.
That is it.
So why don't you just go ahead and write that?
Now I'm going to show you why on this next one. It's going to take a minute, but we're still good on time for our quiz. So number 3 is going to be kind of a proof for the fundamental theorem of calculus. And some people, when they see proofs of theorems, it really does help them remember. Some people don't care. Sorry if you're one of those people. I'm going to show you that it really is true. So we are going to let g of x be the integral from 1 to x of 3t plus 5 dt. We're going to find a formula for g that doesn't include integrals. So let's graph it. So 3t plus 5 is going to be a line. So I'm just going to draw a straight line. It's not to scale, but that's okay. Okay, we're gonna add up the areas from when x is 1 to when x is x. So that's going to change from whatever you put in. What shape does that make? A trapezoid. Now we know how to find the area of a trapezoid. You may not like it, but you know how to. So you add the bases and you divide by 2. And then you multiply that by the height. Now the height is, we can think of the trapezoid being on its side. So this is the height, and then this is the base, and this is the base. So we need to find those.
Which ones are the bases?
The parallel lines. So this is the base, this is the base, and this is the base. Oh, might not be able to find them. Okay, so what is the height? What is this base? The length of this base when x is 1.
3t plus 5 dt.
It's
Huh?
3 times 1
Oh,
plus
8.
5, 8. So that's going to be the 0.18. So I know that's 8. Just put 1 in. Alright, and then to find this height, we basically put x in. So that's going to be plus 3x plus 5. Okay, so what is this distance? Technically the height, I think of it like the width.
1 plus x.
Close.
Minus x
1 minus
minus
x.
x.
Oh, x minus 1.
X minus 1, yeah.
Yes. So this whole distance is x. Take away the distance that's 1. That gives you x minus 1. I keep wanting to say it backwards. Okay. That technically is a formula for g of x. It doesn't include integrals. Now, I see that in part B, I'm going to have to find the derivative of that. So I'm going to make it easier to look at and easier to find the derivative. So I'm going to go ahead and add my 8 and my 15. Oh, I'm gonna add my 8 and my 5.
Oh.
I just said the wrong number. And then I'll multiply those together. So multiplying across the bottom, or the denominators, that's going to give you 2 down there. And then we'll just distribute on the numerators. Alright, and then one more step. I'll divide all of those by 2. Okay, so you guys, we haven't done this in a while, so go ahead on B and find the derivative of this, please. Does that look familiar?
It's the thing that was in the other thing.
Is the integrand. That was in the integral, but with an x, right? Instead of a t. So what theorem does that look like?
The fundamental theorem of calculus, part 1.
Absolutely. That is straight up the fundamental theorem of calculus. So, and that's what we did. We found the derivative of an accumulation function. We just went about it in a different way, and we ended up with what we were supposed to. So, the derivative of the accumulation function is the integrand with an x. Okay, so our assignment today is actually going to be out of the book, which we haven't done anything out of the book in a long time. But there's a question I want you to change, and then there's one I want you to add, just because the book doesn't do exactly what I want it to. But on page 290, I want you guys to do number 74, but I want you to change 74D. It tells you to do some kind of graph. Don't do that graph at all. All I want you guys to do is find G prime of 2 for 74D. And then you're going to add a 74E. There isn't a 74E. I want you to find G double prime of 3. Right? And then I just want you to do 81 through 86. Now 81 through 86 is going to take you maybe 3 minutes. It won't take long at all. Alright, so